Hey everybody, welcome to this lesson on project management. So this is going to be a two-part lesson. Here we're going to get into the main part of project management, what it is, how it works, what are the two different kind of systems. Lesson number 2 will be all about crashing. So that's kind of a separate topic on its own. Before we get into it, if you enjoy this lesson, please go ahead and hit that subscribe button. It helps me with the algorithm, and it'll let you know if ever I post more material. Okay, so let's get into this. So project management. Now, project management can be applied to pretty much anything. It can be applied to building a home, if you're a contractor. It can be applied to, a legal defense, if you're a lawyer. It can be applied to a school project, if you're a student. What we're looking at here are what we're going to look at is how do all of the activities that form a project come together. And that's really what a project is. A project is just a sequence of activities or activities that have to be completed in a particular sequence in order for the project to be completed, right? Think of building a home. We need to dig a hole, we need to lay down the foundation, put up the walls, put on a roof, paint it, landscape it, right? All of these are the different activities that have to be completed before the home is done. Now, some of those activities have to wait, right? Like I can't put on the roof until I've put up walls, while others can be done right away. I could probably start, working on the yard, even if I haven't completed the put up any walls or put on the roof. So that's essentially what a project is. Now, what we're going to be looking at in this chapter is how do we deal with managing those activities. And there's really two systems. There's the CPM, or the critical path method. This is so the main thing you'll notice is that the difference between these two is the time duration. So one of them uses what we call deterministic times, meaning fixed times. Every activity takes an exact amount of time. And for this one, really what we're optimizing for, or what we're focusing on, is optimization. Okay, you'll see what I mean in a moment. Whereas later on, we'll see the PERT method, the project evaluation and review techniques. This uses probabilistic time estimates, where time is variable, where the same activity could take you 2 weeks to complete, 3 weeks to complete, 5 weeks to complete. There's a little bit of variation there. And in that context, what we're typically focusing on is time management. So time is not an issue with the first system because time is fixed. There's no variation. We know exactly how long it's going to take. Whereas in the second one, time becomes a variable. So now this is called a precedent network, where we see every activity. So every node, every circle here that you see, every letter represents an activity required to complete this project. Every unique way that I can get from start to end is called a path. So for example here, the AC is a path. ADE is a path, right? AC, ADE, and then I've also got the path BE. Now every path has to be completed in order for the project to be done. Okay, it's not like these are alternate routes to get to the end. These are all paths. Now, why do we have these paths? Well, the paths show us that some activities are independent of each other, meaning they could be started while the other one is happening. It doesn't have to wait for anything, while others have a sequence, right? So when you're looking at this network, you can see that as soon as the project starts, I can start both A and B. So now imagine this is a school project where you guys can start the research, and separate from that, you could also begin writing the introduction. Okay, let's say that you don't need any research for the introduction. The two are independent, but to write the body of the research paper, you need that research. So you see, activity C has to wait for activity A. Okay, let's actually make the body D. Okay, so D has to wait for A to finish before it can be started, and then E will say is the conclusion. You see, you can't write the conclusion until the body's been finished and until the introduction is finished. You see, E is waiting for both D and B. That means B and D have to be completed in order for you to start E. And then maybe C could be, something related specifically to the research, like, maybe rent out books or whatever, right? Doesn't matter. The point is, this shows you all of the activities, the sequence they have to be completed in, and then the little numbers you see on top, that's how long it's going to take for each activity. Oops. So for example, activity A is going to take you, this could be 3 weeks, 3 days, whatever. Let's call it 3 weeks, right? 3 weeks. C is going to take 6 weeks. D is going to take 9 weeks. And with this, we can, estimate how long the entire project will take. Now, I said earlier that you have 3 paths. You can have 3, 4, 5 paths. You can have as many as you want. One path in particular is the most important. It's called the critical path. The critical path is the path with the longest duration, the path that is going to take the most amount of time to complete. And you determine that just by adding up the times of each activity. So for example, AC, that's going to take you 9 weeks. Whereas BE will take you 6. And then ADE, right, that was the third path, is going to take you, that would be 14 weeks. So you see, there's your critical path. Not because it has the most activities, but because it has the longest total time. It's called a critical path, and those activities, A, D, and E, are called critical activities. Critical activities are the activities that you cannot mess with. You can't delay them. If they're late, the whole project gets delayed. And so you really want to focus on those activities being completed on time, whereas the others have a little bit of slack. Slack is time that you can actually afford to delay that activity. Okay, so the first exercise we'll do is about that. You have here the exact same network. I've removed the background because we're going to be writing on this. And I want to show you guys how to calculate early start, early finish, late start, late finish. Remember, the focus here with the critical path method is optimization. And how do we optimize? Well, we optimize by using key resources on critical activities, on key activities. So in order to do that, we first have to figure out, okay, which activities are critical? We already know that. And now for the activities that are not critical, how much slack do we have? Can I delay it 1 week? Can I delay it 2 weeks, 3 weeks, so I can focus on the more important activities, right? So that's what we're going to be seeing here. Early start is pretty self-explanatory. It represents the earliest you can possibly start an activity. If you wanted to start everything as quickly as you can, what would be the earliest so you can start an activity? And then what is the earliest you can finish it? That would be the early finish. Late start and late finish is kind of the opposite of that. If you still want to finish on time, but you want to delay the activity as much as possible, what is the latest you can start it and the latest you can finish it? So we'll start with that. Now, the system I like to use is these little grids, and I make one for every letter, for every activity basically, right? So I've got this grid, it looks like a big H. So I'm going to, I'll make one for each. So that'll be for C, for D, for B, and for E. Okay. And the project always starts at time 0. I'll give you guys a little template here. Basically what I'm going to be doing, early start in the top left, early finish top right, late start bottom left, late finish bottom right. At the top, I typically like to put the time, and at the bottom here, I like to put the slack, S for slack. Okay, so this is called the forward pass method. Why? Because we are passing forward the times from the previous activities. Here's what I mean. The project starts at time 0. So I'm going to pass that forward, and that is the earliest that I can start activity A. And that kind of makes sense. Don't overthink it. What's the earliest you can start the very first activity? Well, right away, time 0. And activity A is expected to take 3 weeks. See, I put the time there. So what's the earliest you can finish it? Well, think of it logically. Early start plus time will give you early finish, right? If you're going to start at week 0 and it's going to take 3 weeks to complete, well, the earliest you could possibly finish activity A is week 3. And remember, it's called the forward pass method, so we're going to pass this number forward here. The logic is, when can I start C, the earliest? Well, you can only start C once A is finished. So the early finish becomes the early start for the next activity. And this is the process. We're going to put 6, right? That would be the time. So the earliest this one will finish is week 9. Now we're going to go all the way back to the start and do it again for every single activity. So D. D we know is going to start only once A is finished. So this 3 gets passed forward here as well. D is, that's wrong, that should be a 3. D is going to take 9 weeks. And so it'll be done by week, what's the math on that? 12. Now for E, you need to watch out. We're not just going to blindly pass forward this 12 here, because there's also B that we need to consider. Both of those are leading to E, so which one are we going to pass forward? Well, the answer is you're going to pass forward the higher number. Okay, when you're passing forward, you have to pass forward the higher one because you need to wait for all of the previous activities to be finished. So before I can do E, I need to go all the way back to the start and do B. So B is going to start at time 0 because, again, I'm passing forward the 0. It's going to take 4 weeks, so it'll be finished by week 4. And now I have my options. Do I pass forward the 12 or the 4? Like I said, when you're passing forward, you pass forward the higher number. Again, just think of it logically. When can I start E? I can't start it at week 4 because D is not finished until week 12. So you pass forward the larger number, add E's time, and you get the early finish. Now, once you've done all the activities, we'll look at the longest path. The longest time determines the length of your project. This 14 is the length of your project. And we already knew that, right, from here. So this is how you find early start, early finish for every activity. Okay, now, the next thing we'll show you is called the backward pass method. We're going to do the same exact thing we just did, but in reverse. So going from end back to the beginning. So let me clear out some of these arrows. Okay. The goal now is to finish within 14 weeks, but starting every activity as late as you can. So what that means for us, this 14 is going to become the late finish for every activity at the end. So activity C has to be finished by week 14. And if it is, the project will be finished on time. So now you're going to do late finish minus time gives you late start. Again, think of it logically, right? For activity C, which is going to take us 6 weeks, to finish it by week 14, you have to start it by week 14 minus 6 is 8. So this has to be started by week 8. Same thing goes for this one here, E. E has to be finished by week 14. If it's going to take 2 weeks, it has to be started by week 12. Now take a look at the difference here. For activity E, there is no difference between the early and the late figure. Why is that? The reason is because E is a critical activity. And the difference between the numbers at the top and the numbers at the bottom, the early and the finish and the late, is called slack. You see here, E has no slack. I'll put a 0 there. Critical activities have 0 slack. They cannot be delayed. Slack time represents the amount of time that I can delay the activity without delaying the project. But if you look at C, C has 5 weeks of slack. You can look at the difference between these numbers. You can look at the starts or the finishes. It doesn't matter. The slack should be the same. 5. I can delay it by up to 5 weeks. Okay, let's keep working back now. So this is called the backward pass method. So now the start here gets passed back and goes there as the finish. So the late finish for A is 8. It's going to take 3 weeks. So 8 minus 3 is 5. And there's 5 weeks of slack again. Now you want to be careful here because activities that are on the same path, they don't have separate slack times. The slack times are actually related. They share 5 weeks in this case. It's an important thing because we often look at this and we're like, okay, I can delay activity A 5 times and I could delay activity C 5 times. It's not and. They share the 5 weeks. So, which means if you were to delay activity A by, say, 2 weeks, well, C could only be delayed by another 3. The total slack time is 5. Activities along the same path share their slack. Okay. So let's keep working back now. D. Actually, I made a mistake here. I just realized I couldn't actually complete A. Not yet, anyways. Why? Well, because there's two activities that go back to A. So I'm gonna edit this out, actually. Fuck. Now, before I can do A, I need to complete D. It's kind of like before. Because I technically have both C and D that are going to A, if you're coming from the back, then we need to complete these. So D, you're going to pass back, this is called the backward pass method, the 12, and put it there. D has to be finished by week 12 so that E can be started by week 12. And then 12 minus 9 is 3. And you see this one also has no slack time because D is another critical activity. Now we can do A. So you have to decide, am I passing back the 3 or am I passing back the 8? Now, when you're passing backwards, listen up, you pass back the smaller number. When we were passing forward, we had to pick between two, we passed for the higher number. So here we pass for the smaller one. Pass backwards the smaller one, so this goes here. That's the 3. Again, the logic there is this has to be 3 so that D could start by week 3. If you were to pass back the 8 and activity A finished at week 8, well, D would be delayed. 3 minus 3 is 0. So activity A is another critical activity. It has no slack time. And now we're just about done. We just have to finish B. So B is easy. It's coming from E. So we're going to pass back this 12. 12 minus 4 is 8. This one has 8 weeks of slack time, right? The difference between these two is 8. So activity B can be delayed up to 8 weeks without hurting the project. So here it is. This is how you find early start, early finish. Now let's see if we've answered the questions. What is the critical path? We said before it was ADE because it was going to take 14 weeks, which was the longest path. How long will this project take? That's 14 weeks. Determine the early start, early finish, late start, late finish for each activity. That's now done. Okay, take a good look at that. If you have any questions, leave them in the comments, and let's move on. The next technique is called the PERT, or the Project Evaluation and Review Techniques. This one is where the main difference here is that your time is not fixed. It's variable. You have what we call the optimistic time, which is your best case scenario for the fastest time that you can do the activity. Most likely, which is the most likely, right? What the time that it usually takes. And pessimistic, the worst case scenario, right? If everything goes wrong, this is how long it could possibly take. So we're introducing variation. And what we're going to be looking at in this part of the chapter is how to calculate things like probabilities, right? Now that time is not certain, the amount of time it takes to complete your project is not certain. So you have to be able to calculate, well, what is the probability of finishing a project, within before 10 weeks, before 15 weeks, or something like that. So you've got several formulas here that we're going to be using. The first one is the expected time of the activity. The expected time of the activity is the optimistic time. The expected time of the activity is the optimistic time plus 4 times the most likely plus the pessimistic time divided by 6. Think of this as the average amount of time it takes to complete this activity. Then you've got the variance. You take pessimistic minus optimistic divided by 6 squared. And if you don't square it, you get the standard deviation of the activity, just like you would in any stats class. Then, for the expected time, variance, and standard deviation of a path, well, for the expected time and the variance, you add up the individual activities, right? So for the expected time of the path, just like we did before, you're going to add the expected time of each activity. So the sum of the times. Same for the variance. If you want to know the variance of a path, you add up the variances of each activity. It's only for the standard deviation that you don't do that. The standard deviation is found by square rooting the variance. Okay, so we're going to do this exercise here. We're also going to see here how to deal with a table like this where you have to draw the network yourself. It's really simple. You just want to be a little bit careful when you're drawing it so you don't put your lines in the wrong place. So we have here the list of activities and then the predecessor, which means what? The predecessor comes before So when you see something like this, it means that activity A is going to go to D. Activity A is going to go to E, and so on. So any activities that don't have predecessors, they're basically preceded by the start. So those are your first activities. So we're going to start here, put S for start, and we've got A, B, and C. A, B, and C. You can put circles around them if you want. Okay, there you go. Let's just center that a little bit. Great. Then A goes to D and E. So I know that I've got both D and E coming after A. So that's good, that's good. F. F comes after B and E. So I'll put F here. Actually, I'll move it a little bit. Bring it here. So both E and B go into F. That's done. C goes to G. Like this. F and G both go to H. Like so. And you've completed everything. Double check it. It's good. Once it's good, any loose ends, I call them loose ends, basically any activities that are not going somewhere have to go into your end like that. Boom, done. So we have our project. Next, we've asked you to calculate the expected time and the variance for each activity. So for this, I'm going to show you how to do it. I'll start with activity A. So you have all this, right? I'll just bring it here so I can work with it. It's being weird. Okay. Okay, got it. So for the expected time, you're going to take the optimistic time, so 2, plus 4 times the most likely, so 4 times 4, plus the pessimistic, all that divided by 6. And if you do the math, you're going to get 4 weeks for that. So it means that activity A will take on average 4 weeks to complete. Then we want to find the variance. So for this you take, and again, the formula I'm using, if I just go and grab them so we can see, I'm using these two formulas right now. Okay, so this was the first one. Now I'm using this one here. So pessimistic, which is 6, most optimistic, which is 2, all that divided by 6, and then all that squared. So 0.44. That is our variance. And you would be doing this now for every activity in your table. Okay, so we're going to use a little bit of movie magic here. Okay, so after you've used these formulas over and over and over again for each of your activities, you should have these values. 4, 5, 7.17, 3.17, and so on. Now, if you want to find the standard deviation for an activity, there's really 2 ways that you can do it. You can follow this formula, which is basically the same formula as this, just without the square, or you could square root your variance. So if we look at activity G, the variance was 0.25. You could just square root that, and you would get your standard deviation. So the square root of 0.25 is 0.5. Great. Now, if you want to find the expected time and standard deviation of each path, we're going to do this one manually because you really only have 3 paths. So you have your paths. So how many paths do we have? I see actually with more than 3. AD, that was one of them. I see A, E, F, H. A, E, F, H. Then I see B, F, H. C, G, H. And here's where you want to just, even though this step is easy, you just want to be really careful because you don't want to miss one. That's bad enough. And if you happen to miss the critical one, then you're in trouble, right? So just double check. Okay, AD good, AEFH got it, BFH got it, CGH got it. Okay, great. So these are my paths. I'll paste that here. So I'm going to have really three columns: expected time, variance, standard deviation. So for the expected times, for this, we're going to use this little table here, and we're just going to add up all of the activities along the path. Okay, so for AD, we're going to add up A and D. So that together would give us 7.17. And if we added up their variances, that would give us 0.69. The standard deviation is just the square root of the variance. So this would be the square root of the 0.69, which should give you about 0.83. Again, depending on how you round it, maybe you're getting slightly different answers. I'm keeping about 2 decimal places here. You feel free to go more or to go based on what your specific teacher kind of requires. Then you have AEFH. So A, E, that's 6, F, okay, now we're at 17, and H, so 27. And then same thing with the variances. So this will give you 1.11, and if you square root that, it should give you about 1.05. We'll do this for all of them. BFH, so B, F, and H, 26. A variance of 1, and of course the square root of 1 is 1. And CGH, 27.33. So there's your critical path. We don't typically talk about critical paths in this method, but there it is if ever. Then the variance, if you were to add up the variances for CGH, you get 0.94. And then if you square root 0.94, you get about 0.97. Okay, so that is how you answer that particular question. And the next thing we're going to see is probabilities. So we're going to start a new question. Now, here you've got kind of a different setup, right? We don't have a network or anything like that. We actually have just like a summarized table. So we have a project with 4 paths. They're all independent. Independent paths means they don't cross. Like if I show you, these are not independent because you have some activities that are on 2 paths. An independent project would be if every activity, imagine a project that looked like this. A goes to B, and that goes to the end. And then separate to that, you have C going to D. And then separate from that, you have E going to F, right? Where every path is completely independent of the other. That's what we mean by independent paths, okay? You have their expected times and you have their standard deviations. So we're going to use something you would have learned in your intro to stats class to solve this. Now, to find the probabilities, one of the assumptions we make is we assume a normal distribution. Just, it's not something you need to do kind of actively. It's just one of the underlying assumptions of what we're about to do. We are estimating that all of these durations are normally distributed. And so to answer a question like, what is the probability of completing this project in less than 16 weeks, we need to find the probability of every path being completed in less than 16 weeks. Because the paths are independent, we're going to do this for each of the paths, and then we'll multiply it all together. Okay, so now we're jumping ahead a little bit, but let's break it down. We'll start with the first path, path number 1. Now remember that we're assuming a normality, and what we learned in our intro stats class is that if you take a bell curve, the expected time is basically your average, right? Think of that as your mu. So that would be your 14.5. That's what you put right there. And we're trying to figure how long, the probability of it taking less than 16 weeks. So 16 would be here. So the probability would be this area. So we're going to find our z-score, and for z-score you're going to take x, which is the value in the question, minus your expected time over the standard deviation. So 16 minus 14.5 over 2.2. So 16 minus 14.5 divided by 2.2 is 0.68. This is a z-score. We're now going to look this up in our normal distribution table or your z-score table to find the probability that corresponds to this value. Okay, so here we have the two possible z-score tables depending on which one you use. On the left-hand side, you have a two-sided z-table. Two-sided meaning that you have a positive page and a negative page. Or maybe you use a one-sided table where it's just absolute value, so there's only a positive side. So I'll just quickly show you on both how, and you know, you use the one that you want to use or that your teacher requires you to use. So we had found 0.68 as our z-score. Now, if you use the two-sided table, you're going to go look up 0.68. So 0.6, and then the second digit is your column, right? So 8 would be over here, and look up the intersection. So that gives us 0.7518. This is the entire area to the left of your x. When you use the two-sided table, the table gives you the entire area to the left, 0.7518. Now, if you use so I'm going to write that down, 0.7518. Now, if you use the one-sided table, it's pretty much the same, except the difference now is that the table gives you the area between your x and your midpoint, or your midline, in this case, the expected value. So if we look up 0.68, you're going to find 0.2517. Or 0.2518. So these are slightly different tables, but basically the difference between the table on the right and the table on the left is 0.5. Because if you look at the images, right? One of them stops at the middle, so it tells you the area between, and one of them goes all the way to the left, so it tells you the whole thing. So again, there isn't a right or a wrong one. It really depends on which one you use. Okay? So in either case, if I'm looking for the entire area to the left, this one gives it to me directly, which is great. This one, on the other hand, I'm going to have to add 0.5. I want the entire area to the left. So now I know that this is 0.7518. Either because I used the double-sided table and it gave me that directly, or I used the one-sided table, found that this was 0.2518, and then I added 0.5 because I know that half the bell curve is always 0.5. So the probability that x is less than 16 is 0.7518, but that's only for the first path. We're going to repeat that process for every single one of these paths. Okay, so I'm not going to draw the bell curve for each one. I will draw it for path 3 though, because you'll see something a little bit different there. Okay, so let's go with number 2. So x, in this case, is 16 still, but the expected time for path number 2 is 13.7, and the standard deviation is 1.15. For path 3, 16, that's my, the question. 17.4 is my expected time with a 4.32 standard deviation. And then path 4, 12.4. So 16 minus 12.4 over, what was that, 2.88? Okay. So 16 minus 13.7 divided by 1.15 is exactly 2. 16 minus 17.4 divided by 4.32 is negative 0.32. So that one's special, right? You get a negative z-score. 16 minus 12.4 divided by 2.88 is 1.25. And now we're going to go look these up. Now, of course, if you have the option, I recommend using the double-sided table. it's just better. It takes a lot of the guessing out of it. So if we go to that double-sided table and we look up the number 2, well, we're going to find 0.9772. That's perfect. That is the entire area to the left. But if you go to the one-sided table, you're going to find 0.4772. And then you want to add 0.5 to it. Ultimately, the two should be the same. It doesn't matter which of the tables you're using. So 0.9772. That is the probability of x being less than 16. Then we had negative 0.32. So this is why I like the double-sided table, because it has a negative side. So negative 0.32, which would be this number right there. 0.3745. Now here's the thing. If you get a negative number, you're going to use the right-sided table, the one-sided table. Listen up. You're going to go to the absolute value. So you're still going to go to 0.32, which is here. But this time you're not adding 0.5. Okay. If you get a negative z-score, you need to subtract this from 0.5, right? So now you're going to be doing 0.5 minus 0.1225, 0.1255. So that gives you 0.3745. And you see it is the same, but you have to remember to subtract it from 0.5 when it's a negative number. Okay. So that's part of what you have to learn if you're going to be using that right-sided table. Let's go back to the, so 0.3745, and now 1.25, positive 1.25, so 1.2 and 5, 0.8944. Okay. So we have the probabilities now for every one of those paths. So to know the probability of the entire project being completed on time, because these are independent, you need to multiply each of these. Why? Well, think about your stats class. When you want to find the probability of 4 things happening, you need to multiply each one of their probabilities when they're independent. So I want this to happen, and this, and this, and this. So if I do that, the probability of the entire project being completed within 16 weeks is 0.2461, or about 24, almost 25%. Part B here, really easy once you've done part A. The probability of completing a project in more than 16 weeks is just 1 minus that. So 0.7539. And that is always how you complete the probability of more than. Even if I had never asked you A, and this is what I'm trying to say, okay, and you really click with this. Even if we didn't ask you A, we just asked you B, you would have still had to complete A. In order for you to tell me the probability of more than, you first have to tell me the probability of less than, and then subtract that from 1. Do not find the probability that of every path taking more than 16 weeks and then multiplying that all together. It sounds like, why not? If you could do it for less, why can't you do it for more? But it doesn't work that way. Because if I asked you the probability that the project is completed in more than 16 weeks, I'm not saying what is the probability of all the paths taking more than 16 weeks. As long as one of them took more than 16 weeks, then the entire project would take more than 16 weeks. So it's not the same thing. It's not the same thing as saying what is the probability of all the paths taking more than 16 weeks. So please, whether we ask you less than or more than, your first step is always less than. And then if you want more than, take the complement, right? Do that, subtract it from 1, and you'll have your answer. Great. So if you enjoyed that lesson, please hit that subscribe button first of all. If you want to watch all the lessons for all the different topics on operations management and you want to do some practice exams, head over to profjohnk.com and you can sign up for the various lessons there. The next lesson we're going to be doing is crashing, where it's still in line with project management, but now we're going to be looking at how do we shorten the project. Okay, it's going to take 14 weeks. What if I want to do it in 10? Where can I spend a little bit more to speed up the process. So I hope you guys enjoyed the lesson. Hope that it was helpful, and I'll see you at the